Okay, we're going. All right, so tonight's class is going to be about, where's that? Mounts and telescopes. Now, of course, we've discussed a lot of this before, so I think I told you in the beginning of the class that sometimes we're going to do some rehashing because there's so much material to cover um, and you have to know a lot of stuff up front, so or get a lot of stuff up front. So we'll go through and do a little more thorough uh, talk about the mounts and telescopes. We're also going to talk about multiple star systems and deep sky objects and techniques for finding deep sky objects. So let's get started. Oh, also just as an update, I'm going to update this document and the lab document tonight. So tomorrow morning, the latest version will be out. It's not much difference, but just to let you know, the website will have the latest version of it. So there's essentially two types of telescope mounts. There's the Alt-Az mount, which is this light here. Let me increase the size so you can see that, which goes up and down, left and right. Pretty much follows the compass in motion and goes up and down. And then there's equatorial. And actually, an equatorial mount is basically an Alt-Az mount, but put on a angle to meet your latitude, yes, and pointing towards the North Celestial Pole. So its motion is not nearly as intuitive as the Alt-Az mount, but you guys probably realized that when we went through in the lab and showed the different telescopes mount and stuff. So the pros of the Alt-Az is easy and intuitive to operate. Setup is easy and quick. Usually all you have to do is plop it down, level the mount, and sometimes you point it north, if there's markings on the mount, but most of the times, for most of them, you don't even have to worry about pointing it north. Unless it's a go-to mount, then you might have to have a different specific orientation you have to put it. The cons of that kind of mount is it doesn't follow objects in the sky because you have to have two motions to follow that objects in the sky, unless it's computer controlled. But even then, the computer isn't going in one smooth motion. It goes, two motions at a time. But that's transparent to you. You don't see that. Not easy to use with star charts. If you're using the Alt-Az coordinates, it doesn't apply to star charts. Star charts are based on the equatorial type of design. Not many people use star charts anymore, though, so that may not be an issue. And that's what I was saying. Applications can eliminate that issue because applications do those conversions for you. Generally, this type of mount is not going to be good for deep sky astrophotography. It may work fine for planetary imaging, but deep sky astrophotography is by far dominated by the equatorial mounts. Although, yeah, so I'll just leave it at that. Once the object is located, keeping the field of view can be a bit more work because you have two axes to control if you're manually operating your telescope. Okay, so what about the equatorial mount? It follows the objects in the sky as once located if there's a clock drive included. And a clock drive, generally, this is kind of old school stuff because generally you're going to either have a go-to mount or else not. Although some of you guys, I think, maybe had a fork anyway with the clock drive. And basically all it does is go in one motion. So it depends on you aligning up that mount to the North Star. It's pretty easy to follow an object if manually tracking. All you have is one axis to adjust. And the star charts are easier to use with these mounts because the star charts are based on the equatorial system. The cons of it is the motion of the mount is not intuitive. Pointing to an object isn't just a matter of slewing up and over. You have a motion that's diagonal instead. So it can be a little more tricky to find an object using that. Setup will take longer since you need to point to the North Celestial Pole. And of course, I mean, it can go pretty quick. If you're just doing visual observations, you can generally just kind of guesstimate where the star is or, aim it in the general direction and it'll be good enough for visual. Where it becomes critical is if you're imaging or want to track for a very long time, then you have to be more precise on how you do the alignment with the North Celestial Pole. And different telescopes have different reticles. A lot of them will have reticle going through the telescope mount, and you have to orient it based on different parameters there. Any questions on the various mounts? Two types of mount. So I guess why we're here talking about this stuff, so you might ask yourself, we're going to hit the different types of telescopes, but there's also Dobsonian telescopes, but those are just the alt-az mount as it is anyway. It's just up, down, right, and left. So even though the mount may not apparently appear like alt-az or equatorial, they basically do boil down to those two designs. As far as I know, those are the only two designs out there. Okay, so there's single axis, dual axis, and go-to telescopes. Again, most of the discussion on single axis and dual axis is old school stuff, because now the go-to telescopes, if you're going to spend any extra money, the go-to telescopes are so cheap that it doesn't really pay to have a single axis or two axis motors on them, because they're fairly yeah, they just don't make them anymore because the go-tos are almost as cheap to make. So what is a single axis telescope? It's basically a clock drive. So if you have an old telescope like a fork drive, again, it's just going in one motion. Dual axis is basically the same thing. It has that clock drive. Plus, you may have a controller that you control let's see. So the clock drive is going in the right ascension. The other drive would be in the declination. Again, you're not going to run into these unless they're old telescopes. The go-to telescope drives are basically calibrated at the beginning of your session. You point to a number of stars. You know, the computer usually will guide you which stars, or else you point to the stars and tell it you're pointing at specific ones. And then once you've done that, the telescope's ready to point to any object you want. So with go-to telescopes, the learning curve is all up front. Learning how to calibrate that telescope can be challenging if you don't have someone there to help you out with it. I know when I got my first telescope, it was took me about 6 months to figure out how to use the thing. Every weekend, I'd spend a couple hours out there playing with it. Finally got it figured out. So those are the go-to telescopes. And here's some examples of the different types. Here's an example of the clock drive on a little cheap telescope, and then a go-to on alt-az mount and the equatorial mount. Questions so far? Okay. Optical tube assembling. There's a number of different designs. There's three more popular designs out there, but there are definitely more than just these three. So I'm just going to review these because we don't have time for all those other kinds. There's a refractor telescope, which takes light and bends it through a series of lenses. This is the same type of telescope as Galileo. Now, this is the first design of a telescope that Galileo used. It has a big lens in the front, light goes back here, and then there's another lens where the eyepiece is at. You know, there's that diagonal in there. Sometimes you have to have a diagonal if you don't want to, but diagonal and the eyepiece, and then you view your object. The nice thing about this design is it basically doesn't need collimation when you buy it. It's supposed to be excellent for viewing planets and the moon if the optics are good. There's a lot of refractor telescopes out there that the optics are not good, and what happens is the different colors come into focus at different places, so your colors won't line up on the object you're looking at. So good expensive telescopes can get some excellent planetary and moon viewing, but the cheaper ones are not so good for that. This is not a cost-effective solution for deep sky viewing because basically they're limited to about 5 inches before they really start getting expensive and really, really expensive. And I think the biggest one you can commercially buy that's mass-produced would be like 7 inches, and those are fairly rare as it is. And because of the design, they're very long tubes. Because of that design, they become very unwieldy and heavy when they start getting large. Any questions on refractor telescopes? I hope I'm not boring everybody. Everyone's taking off their screens, so I'm wondering if they're snapping over there
Well,
or eating dinner or something. All right. The reflector telescope. This is the reflector telescope was designed by Newton. This is a much more cost-effective telescope. This is Isaac Newton I'm talking about. Where the light comes into primary opening in the front, it bounces off a mirror on the back that's a parabola shape. And then it goes forward and focuses or is narrowed down to the secondary mirror and then shot up to the side to the eyepiece. This is a very cost-effective design. Creating a large mirror is much easier and cheaper to do than creating a good lens. So these telescopes tend to be the cheapest you can buy, and I'm not saying there's anything wrong with cheap. These are great for if you can get a nice big Dob. If you're looking for deep sky objects, usually a Dob is what you want. As you guys have seen that's gone to the lab, that's what Benjamin has, or Ben has. He has like a 16-inch it is, and a 12-inch, I believe was the other one. Is that right? Yeah, 12-inch. So these are great for deep sky. You just can't beat them for the price. The downside of it is they're not very portable. They're long. I think I told you guys about, maybe I didn't. When I was down in Chile, we rented out a 20-inch telescope from the guy that we were staying with. And the 20-inch telescope literally had a ladder, not just a small ladder, but I think it had like 5 or 6 steps I had to get up to get to the eyepiece so I could see. And if you're not very comfortable in nighttime climbing up ladders, it's probably not the deal for you. But man, the sky objects that you could look at were just amazing. It's unfortunate that Ben is the last lab that he can attend with us will be next week. He's doing 3 labs, and when we're going out to Picket Post, which is a dark area, he's not going to be with us. He's going to be in Germany with his mom, visiting family, which is a shame because that's when that Dobsonian, that 16-inch, he would have brought that out, can really show you some pretty neat galaxies and stuff. So it's a shame that he won't be able to make that. This is also not conducive to taking photographs. Generally, it's difficult to take photographs with it, although people do some planetary imaging with it sometimes. They also need collimation on a regular basis for the best view. Any questions on the refractors?
I did have a question about the refractor. You said that the refractors usually cost more. Is that because of the lenses? It's more expensive to ground those lenses?
Yeah, a real good lens or on the refractor, not reflector.
Yeah.
I always confuse the terms. It is very expensive to make. So yeah, they're probably the most expensive per inch of the telescopes, per aperture inch that you can get.
Okay, cool, thanks.
But you can get cheap ones. But then what happens is just like with the prism, how the light breaks up into different colors and spreads out. That will happen if you have a cheap refractor. You'll get it won't look the same, but you'll see, maybe on the outside of the image it might look a little red. On the inside it'll look a little more blue and stuff. That's because the light's not being compensated for. Now you can get lenses in the telescope design that will compensate for that. But again, there's the cost. A real good refractor can be quite expensive. All right, good questions. Any other questions about reflectors or refractors so far? All right, let's move on to Schmidt-Cassegrain. You guys have probably noticed I kind of tend to like these the most, although I will say that, and we don't talk about this in this thing, but the what are they called? Massatoff Cassegrain, which is a very similar design. I'm starting to really enjoy those. So let's first talk about the Schmidt-Cassegrain, and then I'll explain what the Massatoff Cassegrain is and the difference between the two. And we'll go on from there. So the Schmidt-Cassegrain is kind of the combination of both of these up here. What it does is on the front here, you have what's called a corrector plate, which is a fairly thin piece of glass. that bends the light a little bit, and then you got a primary mirror in the back that reflects it just like a reflector telescope and shoots the light forward. But instead of having a mirror that shoots it out the side here, it has a mirror that shoots right back into the back of the tube because of there's a hole in the middle of this mirror here that the light goes into and then hits the star diagonal to the eyepiece. So what this is doing is makes it very compact because it's folding the light. So the size of this telescope that it would normally be if it was a reflector is cut into half because it's taking that light, bouncing it back, and then bouncing it back again. So that's why these telescopes, for the aperture size, are much shorter than what you'd expect from a reflector telescope. So they're really nice and compact. They're kind of one of those telescopes that they're jack of all. They do quite well for planetary imaging. They're fairly cost effective for deep sky objects. And they're just good all around telescopes. The downside of them is they do need to be collimated periodically. Not as much as the reflector telescope, but it does need to be collimated. So that's the SMIC Cassegrain. Before we talk about the Massatoff, does anyone have any questions about that type design? Okay. Matter of fact, I think everybody here has a SMIC Cassegrain, right? So there you go. It's a great design. So what's the Massatoff? The Massatoff looks, if you were to look at this, it's identical design or drawing would be identical, but the difference between the Massatoff Cassegrain and the SMIC Cassegrain is the Massatoff Cassegrain has a huge corrector plate up here in the front. It's doing a lot of, and I don't know all the details, but it's doing a lot of the correction right up here in the corrector plate. That corrector plate literally is about as heavy as the primary mirror in the back. So it's actually well balanced. With the SMIC Cassegrain, the back is always much heavier than the front. With the Massatoff, the front is almost as heavy as the back, or they are about the same. So it does a lot of work up here, bounces the light on the primary mirror, and then instead of having, if you guys have looked at your SMIC Cassegrain, you maybe have not looked at it, but if you took that eyepiece or the mirror out of the front, you would see it's a bent mirror. It's a curved mirror, I should say, not bent, a curved mirror. With the Massatoff, it's just a painted reflection. So it's not adjustable. So it's just bouncing the light straight back. Now, the nice thing about the Massatoff is they rarely ever need to be collimated. You can collimate them, and they're supposed to be a pain in the butt. I did have to collimate mine because I screwed it up. Anyway, that's a long story. But I did have to collimate it. It was more tricky, but I think I got it pretty well collimated. I can tell you, even though the SMIC Cassegrain, the refractor telescopes, if you have them collimated, can give you really good images. I swear on my Massatoff telescope, and usually the Massatoffs only get up to like 5 inches because of this corrector plate up here. I have seen them as big as 8, but I don't think they make them any bigger than that. They get really heavy really quick. Anyway, I regularly, on not only my Questar, which is the expensive one, but also on my Celestron Massatoff that I've got, which is a 5-inch that I take out there. You guys have seen it. It looks a lot like a SMIC Cassegrain. That thing, I regularly get the Airy disc on it a lot on both of those, and I hardly ever get the Airy disc on my either. On my SMIC Cassegrain. Now, is that because it's out of collimation? It's probably out of collimation. Well, it must be, but it's just it's not perfect collimation, where the Massatoff's near perfect collimation. Any questions on the difference between the two? What's kind of crazy is that Massatoff that I got, that little 5-inch from Celestron, they sell for about $600 on a go-to telescope. Which is a pretty good price. I have one back here that I got on the auction website that I'm selling for about half of that price. They're just really nice little portable guys. I just love them to death. They're great for in-city viewing stuff. You know, the multiple star systems, planets, the moon, the sun. They're beautiful for that. I would say they're probably one of the best ones. You can get, you know, they say the refractor is supposed to be best for that, but I think the refractor and the the Massatoff Cassegrain are probably almost equal in quality you can get out of them. And these are much more portable. All right. Okay, so there's many different combinations that you can get out of these, these different designs. And those are just 3 of the designs of the optical tubes. There's probably half a dozen designs. There's Razas and all different kinds, but these are the most popular. So many different combinations you can put between the mounts and the optical tubes. So here's an example refractor on a reflector on a tabletop Alt-Az. Here's equatorial mount with a reflector. Here's a refractor on a center balanced equatorial. Oh, that is slightly different. If you look at this one, it's slightly different. It's not just equatorial. This is something Ioptron came up with, which is pretty interesting. It's not just, you see how it has kind of a Z design. It's still equatorial, but it's balanced a little differently. And it's pretty nice design they came up with on that. Here's a Schmidt Cassegrain on a fork. Not a whole lot of those are still out like this with the dual forks. This is the kind that the first kind I had. Mine was an Ultima, but the fork drives with the clocks are pretty good workhorses. They're pretty nice little units. Nowadays, mostly they have the single forks. Here, Schmidt Cassegrain on a single fork. Then here's a refractor on the Alt-Az mount again. And the Dobsonian. Again, the Dobsonian is really just the Alt-Az mount with a refractor on it. And here's another fork. This is a more modern fork of Schmidt Cassegrain. I personally don't like that design too much. I'm not sure why. It's just big and bulky, it seems like to me. But anyway, questions on the different mounts and optical tubes? Okay. Okay, let's talk more about magnification. So what is magnification? I really don't, and I think most astronomers don't pay much attention to magnification. Of course, for people who haven't done much astronomy, magnification seems to be very important. And the manufacturers of the telescopes are always pushing magnification. But really, that's not so important. As a matter of fact, when you're looking at deep sky objects and most of the other stuff besides the planet, sun, and the moon, you're probably going to want lower magnification anyway. So anyway, what is magnification and how do you calculate it? Well, magnification is the focal length of the telescope. Here's an example of a focal length 900 over the focal length of whatever eyepiece you have in here. In this case, it's 25 millimeter eyepiece. So magnification for this combination would be 36. 900 divided by 25 is 36. Another equation I have up here, just the FYI, the focal ratio is the focal length of the telescope divided by the aperture of the telescope. So the focal ratio tells you how fast the telescope is. Generally, that's used for astrophotography. So that's that. What else? General rule of thumb, and I think, general rule of thumb is the 50 times the aperture in inches is the highest useful magnification you can get out of a telescope. Now that's, again, a rule of thumb. It's depending on the atmosphere being good, your telescope optics being, working good eyepiece and all that other stuff. So you may not have as much mileage on that, or you might find out that you can get a little bit more if conditions are excellent. Another limitation is generally, again, the rule of thumb is for typical atmosphere and everything, even if you have a huge telescope that would support higher magnifications, 250 is usually about the most general useful, except unless you're looking at the moon or something like that, you could probably bump it up more. But again, if the atmospheres are really good, you might be able to go up 350 or something like that. Questions on magnification? Right? Here's example 50, 130, 250. So as you can see, as your magnification goes up, typically it's going to be bigger. This is where aperture starts to come into play. Not only does it support higher magnification, but it will make your object brighter. The bigger aperture you got, the more light coming in, so it will brighten up the object. So that is one advantage of aperture on magnification. So again, gotta apologize, but this is a lot of rehash of what we talked about in lab and stuff, but just maybe more in depth is the finder scope alignment. So one of the most important things when you set up your telescope is the first thing you need to do is make sure that finder scope is aligned with the main scope, because the finder scope is what you're going to use to find all your different stars when you're doing that initial calibration. You know, I found with the go-to mount, after you do the initial calibration, you don't use the finder scope, or at least I never do. It doesn't make any difference. But the initial finding the object, it can be very difficult. I don't know if you guys have tried, probably everyone has, to find an object without using your finder scope. Even the sun or the moon can be really hard to find because it's much smaller than you think it is. So getting that finder scope alignment is really critical in being successful early on. And the procedure is basically, you can do this during the daytime. It's easiest. It's find an object like a telephone pole in the back, in a distance, and get your main scope on it. Then adjust your finder scope to it. Then go back to your main scope. Make sure it's still in the same field of view. And if it's not, then you go ahead and get it centered up and do the finder scope fine tuning on there. What is a telescope mount alignment process? It depends on what kind of mount you have, and I already discussed the Alt-Az. Is basically you just put it down, level it up, and you may need to adjust it to point certain directions, especially if you have a go-to telescope before you get it going. There's the Alt-Az go-to. Equatorial mounts, you have to line up with the polar axis. Here's a good drawing of it. So this axis here must be lined up to the north celestial pole. Setting circles. This is, if you have a go-to mount, this really is obsolete. You don't need to worry about it. And I don't think anybody in the class needs to worry about setting circles. But basically, the way you use setting circles is if you don't have a go-to mount, you know where a star is. So you'd find a star like, let's say, not Polaris isn't a good one, but Sirius or something like that, right? Or Betelgeuse. Let's say you go to Betelgeuse, you put it in the center of your scope, and then you look on the chart where Betelgeuse is. Well, this is the coordinates of Betelgeuse. Then you go ahead and adjust your setting circles to that value, and then at that point you can go to your real target, let's say the deep sky object, and point your telescope there using those setting circles. The problem with that is, as time goes by, those setting circles are not being updated. So you need to go to another star periodically every hour or something like that for these setting circuits will be useful to use. Again, nobody uses them anymore, I don't think. Any questions about any of these mounts and alignment on them so far? Sorry, Joe, you were talking about the audio being bad. Is it still bad for you on my?
It's gotten better. I changed networks and that seemed to have helped, although you are hard to hear. I've got the volume turned all the way up.
Jeff, are you having the same problem or?
Yeah, it was kind of cutting in and out a little bit. It was like kind of intermittent.
Okay. Sorry about that, guys. I will check about maybe getting a different microphone or something next time. I'll try to also talk louder. So any questions with anything we've covered so far? All right. Moving on to deep sky objects, changing subject. Okay, well, let's talk about the different types of deep sky objects that are out there. There's open clusters, and that's just a group of stars, basically, that have just recently formed. These would be in nebulas they recently formed and then have lost their nebulas and are starting to disperse throughout the interstellar, throughout the galaxy. But they're still grouped together because they haven't had a chance to disperse yet. So that's what an open cluster is. So they're hot loosely bound gathering of stars. A globular cluster, on the other hand, these are some of the oldest stars in the galaxy and possibly the universe, a group of stars. Definitely the oldest groups of stars in the galaxy. What they are is a sphere of stars that are gravitationally bound together, and they are orbiting the halo of our galaxy. So they do go in and come out of the halo, and they're orbiting around us. These stars are very old, so because they're so old, a lot of them are quite small, or most of them are all quite small, because it's kind of counterintuitive, but the smaller a star is, the longer its life. The larger it is, the quicker it burns through its energy reserves, and it will die quicker. So these are generally fairly small stars. And again, they're gravitationally bound in the sphere. One of the theories, and I don't know how much credence this has, is that some people believe that some of these globular clusters are actually the cores of galaxies that we've consumed, the Andromeda galaxy has consumed, ripped out the rest of the stars around it. And this is just the core of it. So kind of interesting idea. I'm not sure if it's been proven true or not. They're not sure exactly how these things form. And like I said, they're very old stars, so kind of interesting. Next is galaxies. That's just a collection of stars and a vast collection of stars in the ocean of space that are all associated together. They're separated by one another by huge distances measured in millions of light years. The galaxy contains hundreds of billions of stars and can be many thousands of light years across. Planetary nebula consists of a glowing, expanding shell of gas ejected from red giant stars late in their life. So our sun will eventually lose its outer atmosphere and become a white dwarf, and that's the example of this. And a lot of times, let me click on this so you can, let's take a look at the picture closer up. A lot of times, or not, I shouldn't say a lot of times, but sometimes when you're looking at planetary nebulas, you'll actually be able to see the white dwarf that the star originate, or that this thing originates from. It's going to be at the center of your object. You see it a lot when you're doing imaging, not so much when you're viewing it. I have
a question about planetary nebulas. So it's formed from it has a star that formed that gas. And is it called planetary because that gas is expected to gather in certain areas and become planets?
Yeah, that's a very good question. And I take for granted, I don't give the history of a lot of this stuff. So no, it is not. But it's a good assumption. So a lot of this stuff is wrongly named when they learn more about it. When they initially saw these, they thought they might be planets, and so they call them planetary names because some of them were shaped, like a planet. So that's where
makes perfect sense.
Yeah, exactly. More of the history on this is, like I said, our sun will become this at some point. So what happens is, as the sun runs through its energy, or the fuel supply, and I guess let me back up a little bit because this is a beginning class. Although we don't focus on the science part of it, we're more on the observational part. But the cycle of the Earth, or the sun-sized stars, is basically it's mostly hydrogen, or all stars are mostly hydrogen, a little bit of helium and other elements. So what happens is that hydrogen fuses together to form helium, and that process, the two hydrogens weigh a little bit more than the helium, and the helium, and that difference in mass between the two hydrogens and the helium that's been fused together in the core of the star is actually where the energy, goes out as a wavelength of light. So that's why the sun glows like it is. This is the real quick version. And what happens is that hydrogen burns into helium. The helium burns into the next element as a general rule. And basically, you go up the periodic table is what you're doing, building elements. And that's why Carl Sagan said we're all star stuff, because everything in the universe that started off with basically was purely hydrogen. and very small traces of helium. And everything else, all the other heavy elements that we have in our universe, that all comes from stars burning the fuel and exploding, doing supernovas. What's interesting, now I'm getting sidetracked, anyway, but what's interesting is our sun will not do this. Depending on, will not do what I'm going to tell you about. Depending on the size of the sun, it has a different ending cycle. So for ours, which is a fairly small sun, it'll go through a lot of the fuel, and then what will happen was it'll start not burning any more stuff, and so the gas on the outside of it, it becomes what's called a red giant, will start to slowly leave the sun. And so what happens, let me see if I got this right. It's been a long time since I looked at it. So eventually that atmosphere of the sun will come out and actually get the theory is that it'll come close to basically the orbit of Earth. You know, the sun will expand that big. Anyway, so basically the atmosphere just kind of drifts away, and what's left is the hot core inside, and that's that white, and it becomes what's called a white dwarf at that point in time. Does that make sense? Okay. If
Yep.
it's,
Sorry to get you sidetracked.
well, I'm going on sidetracking some more. So if it's big enough, there's actually, I think, 3 different ones. It's been a while since I looked at it. The one everyone interested is if it's big enough, I think it's like 3 or 4 times bigger than our sun. It will keep on burning and do more elements and get to the point where it's burning lead. And when it's creating lead, the next all the elements that are created after lead, actually, instead of being, it's called an endothermic reaction, where it takes more energy to make the element than it does giving the elements making these other ones. So the one up to lead is exothermic reaction. So you get a positive amount of energy out of it. When you're burning lead and other heavier elements, you actually consume energy when you're making those. So long story short, what happens is it starts doing it, and then gravity starts collapsing on it, and then it explodes, it bounces back, and it causes what's called a supernova. And then from the supernova, you get a black hole. Everything collapses down to a black hole. Now, the intermediate in between there is, what is it called? Neutron star. Neutron star is a very dense thing that's left. So there's 3 different endpoints for stars. But anyway, that was really brief and just kind of an outline of the life cycle stars.
Yeah, I appreciate it.
Okay, maybe maybe you appreciate it. All right, on we go. So that planetary nebula. Then we got supernovas, remnant supernova. The Crab Nebula is an example of that. So this thing, when it exploded, all the gas was flying out. So definitely a different ending than the planetary nebula. Here, the planetary nebula is you're going to have that white dwarf in the middle. With the supernova, it explodes and you get a black hole out of it. And of course, you can't observe that directly. Then there's reflection nebulas. These are nebulas where stars are being formed at, and they're not quite bright, hot enough. The stars in here that are being born are not quite hot enough to make the gas glow, but you can see reflection off of the dust and stuff. So that's why it's called reflection. The Pleiades is a perfect example of that. On to emission nebula. This is where some very hot stars, again, sort of like the reflection nebulas. These are interstellar nurseries, or where these are at, just like the reflection nebulas. Orion Nebula is another good example of that, where the stars are acting as the energy source for the gas that's surrounding it. And so it's just like a neon light. Basically, this gas is being energized by these hot stars that are inside it and making the gases glow. And then there's the dark nebula. That's basically very dense regions of dust that's absorbing light. And so what you're seeing, let me pull it up here, is you're not really seeing anything. What you're seeing is the lack of stuff behind it. You know, it's the light that's hitting it from the stars that are behind in this big star field are just being absorbed by the dust in here. And so that's why it's called a dark nebula. That's called a block nodule here, this really dark one. I'm not sure why, but that's what it's called. It's kind of a neat name. This is called the Snake Nebula here. So those are basically the different types of deep sky objects that you can view, and most of them look like fuzzy spots. The planetary nebulas are pretty dense, coarse, and the open clusters are big. They can be, 2-3 times the size of the moon when you're looking at them. And the globular clusters tend to be quite small too, on the order of 2 or 3 planet sizes, depending on what you're looking at. Galaxies, again, pretty small also because they're so far away. And supernovas tend to be pretty small looking too. Open clusters, again, large. And dark nebulas, they can be rather large too, especially in the summertime. You're looking down the middle of the Milky Way into the core of the Milky Way, and you're looking through a lot of stuff, and so you'll see a lot of the dark nebulas looking down that direction. Questions on anything we've covered here so far with the deep sky objects?
James, what would it take to actually look or find a black hole?
So they did that recently with the radio telescopes. They found a black hole and actually imaged it. Because it's so small, they had to group together ones all around the planet Earth, a huge aperture. Visually, the black hole is the lack of light. So you can't ever image the black hole itself, but you can image right around the event horizon where the light goes into the event horizon. I hope I'm telling you everything right. I try to tell you guys that's my understanding. And I'm pretty sure that's right, but science is always changing. So, but yeah, you can't see it directly. Can't be done as far as I can tell. So, but they've gotten, like I say, they've imaged everywhere, and I think that came out like a year ago. I don't know if you guys remember, where they actually did the radio telescope and were able to image basically the accretion disk around the black hole itself. That was pretty neat. So I don't know if that answered your question or not, Adeline.
No, I did.
Okay. Any other questions about deep sky objects? Okay, let's go ahead and start talking about techniques of finding things. And again, we all have go-to telescopes, so this isn't too relevant to us, but it's good to know about the different techniques. Star hopping, which is what I did a lot of when I was in college, and I can tell you that can be very frustrating. I think I wasn't very good at it. I'm sure I wasn't very good at it, because sometimes it would take me half an hour to find something, or I never did find it. It's a combination of not having good technique and then not knowing really what you're looking for and what it's supposed to look like, because they're all little fuzzy spots. So star hopping is a technique of taking stars that let me see if I can click on this and make it a little larger. Yeah, that's not much better, but it is. Taking stars that you know where they're at, and then usually you take a chart and say, okay, I'm going to go from this star to this star to this star to my target. And so you figure that out, and then you go and look in the sky, find the stars, and you may even guide the telescope. Usually what I do would be visually identify the stars, and then start pointing your telescope in that direction. And then just keep moving your telescope around till you identify the object. So that's that technique. It's pretty much like when you guys did our first lab. We use stars to point to where the different other constellations were, or other bright stars were at, and knew where it is. That's kind of the same process. That's star hopping. Let's see. The other one is using what's called Telrad charts. Oh, now this is actually pretty good system. Basically, it's this guy designed finder scope that has these bullseyes in it. Let me see if I can get a better image of it. Yeah, a bullseye in it, like here, and he made a list of charts of where objects are. And again, it's sort of like star hopping. Here's the Big Dipper, the cup and the Big Dipper, and here's the handle. So as long as you can identify where the cup and handle are, you take your Telrad and put the crosshairs or the bullseye in about roughly this position, and your target should be there. And it works pretty good. So that's that. And then there's these setting circles. I just talked about the process of setting circles. You have to find a known star, look up what the coordinates are, adjust these setting circles so they match those coordinates, and then you're able to go to your target. I was never very good at that, and some people say it doesn't work good enough to be useful. I think it works sometimes, but again, go-to telescopes, you don't have to worry about any of this stuff. And the go-to mounts. Basically, all the work involved here is doing your calibration, then you're done. And figuring out how the menus work, right? Any questions about the different techniques being used? Okay. Let's put it all together. So, as you can see, there's many different factors to consider when purchasing the telescope. Most of you guys aren't in the market at this point in time, but it's good to know anyway if you're thinking about buying a different telescope, what kind you want. There are many combinations possible of telescopes and mounts. Something to think about is the budget. What's your budget? What is your target? What is your viewing targets? What do you want to look at? Do you want to look at galaxies, or do you want to focus on stars? Do you want multiple star systems? Do you want to focus on the moon, planet, or do it all? And basically everyone says, yeah, I want to do it all. So this is going to kind of point you to a category what that does. Although Dobsonian does okay too. Portability. This is where Dobsonian is still at. How portable does this need? The best telescope is a telescope that you're going to use. I got that 11-inch telescope in the back that I use for imaging, but it's set up. And as I'm getting older, I used to take it down, break it down, take it up, and go every month out to a place to image, which took me about 2 hours to set up. I'm not going to do that anymore. I'm getting too old for that, and it's just too much work. So I've got it set up in the back, and it's sitting there, and I use it. But if I had to rip it down and put it up every time, I wouldn't be using it much. I can tell you that, because it's just too much trouble. So think about that when you're thinking about it. Aperture is great. Having a large telescope is great, but if you got to lug it with you everywhere you go, you might not do it. Tracking is a thing to consider. These go-to mounts are pretty cool, and certainly the cost of them has become very, very cost effective. Well, actually, that's something on that for the go-to mounts. Tracking is, it following the object in there. So, yeah. Just even considering about tracking, it kind of goes into the mount type. Equatorial is possible to use for deep sky imaging. So if you're thinking about that, you're probably going to be restricted to equatorial, but they certainly aren't easier to set up or easier to use. The go-to mounts that are all pads are definitely easier, but you can't use them for deep sky imaging so easily. And complexity. And the go-to mounts have that steep learning curve, but once you get over the steep learning curve, it's all gravy after that. New or used. You can get some good used telescopes there and typically they'll go about half the price, but you can also get burned. Like I said, the mount that I got, the Loomis Mandy mount, which is a really popular mount, which typically sells for about $4,000, I think I got for, I think it was $1,000, but I probably put another $4,000 into it just to work. That was probably partially me, and I'm still not completely happy with the way it works, but I don't know if, you see, and this is where my inexperience is coming through. I don't know if I'm expecting too much out of that mount or not. It's a good mount, and everyone says it's a good mount, and it tracks okay. But when I'm doing imaging on it, for visually it'd be fine. When I'm imaging on it with a high focal length, I'm ending up throwing away about 2/3 or 3/4 of my pictures that I take. I don't know if a higher end mount, and when I say higher end, we're talking about like $10,000 mount, would be better or not for that type of focal length. So anyway, so list it out. List everything you're thinking about, and try to figure out what's your priorities on it, and then go from there and see what your options are. Questions about any of the stuff I've talked about up to this point? Okay. So here's a practical example. I just took a Smith-Cassegrain. Things to think about, again, when I was talking about the weight and the light gathering power, you want as much light gathering power as you get. But so I thought it would be interesting to put a little curve here together. I don't know if these numbers are valid anymore. I think they're pretty much right. How much you'd pay. So here's the size and aperture, what you'd pay for the aperture size in millimeters, the weight of the optical tube. Now this is just the optical tube itself, and then the light gathering power of that tube. So 4 inches, 5 inches, 6 inches, 8 inches, 9.5, 11, 14. I think the kind of the sweet spot for these telescopes is probably the 6 to 8 inch telescopes. If you're looking for something that you can take in the field with you, because you can look here how the price starts to go up pretty quickly here for these larger apertures. 14-inch telescope, $6,500. But your 8 inches in the neighborhood of $840, 6 inch, $689. The weight also similarly starts to go up pretty quick, 46 pounds for that 14-inch telescope, just the optical tube itself. Where your 8-inch is only coming in at 10 pounds. So the light gathering power, not quite as steep as a curve, but it still goes up pretty good. A 14-inch, you're getting 2,581 times the light gathering power of a typical eye would gather, where the 8-inch telescope is 459. Questions about this little chart here? All right. Then there's references and resources. So there's EVAC observing programs, which I think I pointed out before to you. If you are looking for deep sky, moon, multiple star systems, this is a great place to get a list of different ones. There's a good article about scopes for starters. I think we're all past that at this point. Everyone has a scope that's probably, if you were to go beyond that, this article probably wouldn't be applicable. Same with the best telescope for beginners. Basic telescopes types is where I got some of the information. And basics on eyepieces. If you are thinking about buying a nice eyepiece, this is a good article to read about the different designs and considerations. How much can you pay for a good eyepiece? I paid, decent eyepieces. The Plaus eyepiece seems like a pretty cost-effective design because you can get a decent, and they're pretty decent eyepieces. I think I'd mentioned to you the 40 millimeter from Celestron is it's $50 for an eyepiece, and that's pretty good. Now, if you get high-end eyepieces, I think I've got a 4 to 6 millimeter zoom eyepiece, sort of like the Celestron one, from Televue, and I think it was $350. So you can pay up to $1,000 for a really good eyepiece. That's one thing you do have to worry about when you buy eyepiece from like Celestron or Meade or one of these mass production ones. You may or may not, if you're not sure what you're buying, sometimes you can get an eyepiece that's not very good. On the other hand, if you buy an eyepiece from Badier or Televue, these are premium eyepieces. The eyepiece quality is not going to be in question. It's going to be great eyepiece quality. The question is the eyepiece application that you're using for appropriate or not? More than anything else, you don't have to worry about is it a good eyepiece or not. Astromart is a great little resource for if you're shopping for equipment. You can come here. Let me refresh that. It does cost $15 a year, I believe, to be a member, but you can come in here. Let me log in real quick. Uh-oh. It's giving me this. I hate these things because a lot of times it takes me like 15 times to do it. Plus, I'm going to do this three times. If it doesn't work, I'm going to give up on it. Motorcycles. Why do? All right. Oh, 3 times the charm. You can come in here to the classifieds. And let's say I'm looking for a catatromic telescope. Here's dioptric. Here's all the different ones, and you can sort in here. Like new Celestron 8, E8 for $2,500. Anyway, you can sort here. This has a lot, some really good filters. You can filter just by Arizona if you want to look for things that are being sold in Arizona that you can go pick up. You can filter by models and so forth. There's a ton of stuff in here, as you can see. So if you're looking for used telescope, used equipment, this is not a bad place to start. And like I said, there is a risk with used equipment, but generally if they tell you it's like newer or something like that, you're probably going to be doing okay. The astronomy community is small enough that no one wants to get a bad reputation in general. So if you look at their rating and they're rated good, then you're pretty safe probably. Starzona. So Starzona is located in Tucson, and you can buy equipment from them, and they are very knowledgeable. Matter of fact, the guy that works there, Dean, is the guy that designed this Hyperstar. So these guys, you know, and actually their cost is pretty effective. But these guys really know their stuff. So if you have trouble, especially if you buy equipment from them and you have trouble or questions, they're always willing to help. So they're a great resource, and they're local. So I recommend supporting them if you're looking for new equipment, especially like a telescope. Starzona is a good place to go. And then this is a more popular online. If you want to do online shopping, this one has a wide variety of things to purchase from them. Any questions on anything we covered so far? Okay, so that's the material for tonight. Let's go into the lab stuff. So our lab this week is going to be on multiple star systems. We've already looked at some multiple star systems. The lab is more focused, and this is, you know, you get out of it what you put into it. This is more focused on the preparatory steps you can do to get ready for looking at deep sky objects. In particular, it focuses on star systems, but it would really work for any deep sky objects. So let's go down to it. Night sky multiple stars. Oops. Where'd it take me? Right back to the beginning. All right, I guess that's not working. Let me scroll down. Noon. Lab. There we are. Okay, so what the goal of the lab here is to teach you guys how to figure out what you're going to view for a session. Now, I'm going to show you the process that you can go through, and you might think, "Whoa, that's way too much work." And you know what? It can be. You know, really, if you want to go out and you don't want to put the footwork into it, just go out there, look what's in the sky, see what constellation's up there, and then look it on your application as to what's in that constellation. You're good to go. This process I'm showing you here is if you want to really optimize your session and really get the most out of it possible. So anyway, you don't have to do this, but it's just an example of how to do it. So again, we're going to be talking about double star systems, and this is a real good link here to double star program that East Valley Astronomy Club has. Planet spheres can not use too much, although they're out there because everyone's got their application. But the way you use it is you set the date here is going across here in November, October, and then the time is down underneath it. It's not so easy to see the time on there, but you set the time to whatever the date is, and then it gives you an idea of what's up at this point in time. And here in this example here, it shows, I zoomed in on it. You can see Cetus, TARDIS, Cassiopeia, and so forth. Pegasus are high in the sky at this point in time for that date. And that's the other thing I want to give you a heads up on. This is done in November, and I was thinking about updating it to now, but really what's important is the technique, not really the data so much. And it would be good for you guys to do your own study, so that's why I didn't update it to current. So it's showing that these are the things that are up high in the sky. Now, another way to do it, rather than using the star chart here, is to use this table. And let me explain how you use this, because it's a little confusing when you first look at it, but it's got some good stuff in there. Is it zoomed in good enough so you guys can see the numbers and everything on here? Okay.
Yes.
So, okay, so this is the meridian transit of the constellation. So let's say we're in the month number 5, which is 1, 2, 3, 4, 5, May, right? So what we want to do is look down this column of May, and actually, if you want to look at what's up earlier in the sky, early in the evening, it might be April. May is going to be like midnight, and then June would be going towards the morning time. So really, I kind of pay attention to these 3. Probably more focused on these 2 because, like I said, we're starting to observe early on. Unless you're doing morning observations, you go to June. So anyway, and then this number over here, these rows are the declination. So negative 50 is way down there. Generally, I'm looking at objects that are negative 30 or above up to here. So that's generally what I restrict mine at, negative 30. And honestly, I don't have much of horizon there anyway. So it's usually negative 20, negative 30 is about as far as I'll go. Okay, so we're looking at these rows, negative 30 up to plus 70, or yeah, plus 70, which is really goes up to 90 at the end of there. So that would be the North Star, right, at 90. Is that right? Yeah. Okay, so we're looking at negative 30 up all the way up to the top here, and the months we're looking at are April and May and maybe June. So going here, we can see the constellations up. Puppis is up. Looks like it would be in the morning sky. Lupus is up right at, that's going to be, well positioned at midnight. Libra, I can't remember what the name of this is called. And actually, this is where that potential nova star is at. Corona, I can't remember. I'll have to look at it. I think the other chart. No, I don't have that with me.
Corona
Anyway.
Borealis, I think.
Yeah, that's CRB. This is CRV. I can't remember what that is. Anyway, so another thing, Coma Berenices here, and here's Corona Borealis right here, CRB, and Bootes, Draco. So these are the ones I'd be concentrating on looking at. Right, those are the constellations that are going to be well placed for observing. Does that make sense? How to use this chart? Okay, very good chart to have there. So now we're going to go to planning your observations, walking through the process. And I explain what a star is, multiple star systems, magnitudes we've talked about before, separation. This is another key thing we talked about before, but let's talk about it again because it's good to get this exposure. So separation is the distance between these 2 stars, and it's measured in arc seconds. What I've found for my 5-inch telescope, there's charts, and I think it's going to, we already looked at the chart before in the last class where it tells what, for your size telescope, what separation you can see. Generally, if it's less than 5 arc seconds, it's going to be pretty hard, but probably still possible to do it. Down to 1 arc second, at that point, you really have, you're probably not going to be able to see it. Even in the larger telescope, it's going to be hard. Again, not only is the separation important, but how bright the 2 stars are relative to each other, because a real bright one can just really consume the small dim one in its glare. So anyway, the separation is something to pay attention to because it's going to tell you how hard it's going to be able to see, and the magnitude. So here's a list of 22 interesting multiple star systems. I got this out of the article, and it's actually colorful star systems, I think is what it was listed as. So here's a list of them. So we've got the list of, and I didn't write it down, a list of the constellations that we think are going to be up and high in the sky. So what we do is look for these constellations. Here's Bootes. So this one might be well positioned. Here's Coma Berenices, which is also in that list that I saw. And I know Cygnus, and these guys are coming up later on in the night. So anyway, that's what you do to find this potential objects to look at. Again, our walkthrough, here's a recap of it. Our walkthrough is looking at a different time of year, but that's the idea. So what's the approach to doing it? Is first, eliminate all constellations that are not well placed. Second, consider the brightness magnitude stars, it will be easier to see in the night sky. So obviously, if it's got a very bright star, you'll find it easier. Not so much a concern on a GOTO telescope. Third, consider separation and how far apart they are. Finally, need to order the observations so they are appropriate through the night. So, for instance, we know the sky is going from east to west, right? So when we start our observation sessions, we want to start in the west because that's going to set first. So you start in the west and work your way to the east. That's the right ascension values you have to watch. So let's go through that process. And the other thing to consider is how long is it going to take you to find these objects. Again, with the GOTO, it's instantaneous, or 60 seconds. With a star hopping, it can take you half an hour for each one. So let's go through the example. So an example with the Planisphere, we had identified Cetus, Pisces, Taurus, Auriga. This is all in November. That would be well placed. And then from this list, I went up to that list of stars and found the constellation. Excuse me. Constellation or stars in the constellations that we're interested in. These are the ones I came up with. Then I copied down the right ascension declination, magnitudes of each of them, and the separation. So as you can see, we got 13 arc seconds, 28, 15, 40.9. These are all pretty well separated. Should be pretty easy to see. Now let's look at magnifications. We got 33.5, 7.2. That's pretty good. Since this is 5 magnitudes difference almost, 4 here, 2 here. So these are almost the same, which is good because they're fairly close together. So we should still be able to separate them because they're almost the same brightness, or within the good range here. Same with these two. They're fairly close to the same brightness, and they're well separated. So this should be easy to spot this one. Okay, so I'm going to kind of walk through that on this too. Next is narrow down the list by selecting only 4. We probably keep all identified targets. For argument's sake, we'll go through the list. So for N Cassiopeia, we can see it's a bright star. It's 3.5. So that's well within the visual. You could see it up in the sky. So it's easy to locate in the constellation in the north. There may be challenge resolving the double because it's only 13 arc seconds apart, depending on, of course, all the telescopes that we are using should be able to resolve that 13 arc seconds. Again, another thing that's important is if you're not collimated well, you're not going to be able to resolve, some of these ones that are down to 4 arc seconds, 2 arc seconds and stuff. Because instead of the little area disk you get, you're going to get a smear shooting one way or the other, and it's not going to work right. Okay, so then we look at the brightness difference between the 2 stars is a 3.7 magnitude difference. And that's a 25 times difference. So that the primary star is 25 times brighter than the secondary star. Everyone understand how I got all that information out of these numbers up here? Okay. Adeline, are you with me?
I'm with you.
Okay. How about you, Frank? Are you sleeping over there yet?
I be here.
Okay. All right, on to the next one. So there's Eta Perseus, another bright star, 3.8. So we can see it in the night sky. It's going up to 55 degrees, so it could be pretty high when it's peaked up. And it should be easy to resolve with the separation of 28 arc seconds. However, there's a 4.7 magnitude difference between these stars. So the secondary star will be 50 times dimmer than the primary. So it may be a bit of a challenge to see it. So that's the process we go through. Here's the Delta Cepheus, magnitude 4.1 star. That's getting the limit of what you can see in the city here with the naked eye. This constellation rather easy to locate. Is not one of the brightest stars, but it's one of the main stars that make up the constellation, so that should help. So the difference in brightness between the two is 2.4 magnitudes, which is about 10 times difference in brightness. Also, the separation is 40.9, so it should be easy to identify that. Auriga 14 indicates the rather dim star in the constellation because remember the naming conventions, the star goes from alpha, beta, gamma, all the way through the alphabet, the Greek alphabet. So those are the brightest stars. And then after that, they just start numbered 1, 2, 3, 4, 5. So this is the 14th after the Greek alphabet. So it's a fairly dim star. Its primary star is a magnitude 5. So we wouldn't be able to see it as a naked eye star. Now in the really deep sky, you could see it. So you'd have to blah, blah, blah. Fairly close in magnitude. They're quite close together, so we require higher magnification eyepiece to resolve them. So the point of this is to show you what the reason in, taking these numbers that it's given you in the chart, figuring out what to expect when you go to the eyepiece. Again, a lot of times I don't follow this procedure at all. I just say what's up, pull up my application, and I've got a lot of double stars marked on it, and I'll go, well, let's see what this looks like and look at it. And, if I have trouble seeing a double star, I'm like, well, where is it at? Why can't I see the double star? And then I'll go and look at the application and say, oh, well, these are really close together, less than 1 arc second. So that's probably why the sky's not working out. Or else maybe the other star is quite a bit distant over and I just missed it. So that's that process. Now the final process involved is ordering them. So we identified what we're interested in, these 4. Now how are we going to order the viewing order of them? So we're going to take the right ascension and order it in the order we want to do it. So here we're going to take the right ascension and go, so the RA values increase as we travel from west to east across the sky. So starting at 0 hours, 0 minutes, and 0 seconds, progressing to 23 hours, 59 minutes. So remember, it's like a clock. So we want to look at the right ascension of these and order them. So the first one that's up is 22 hours. That's going to be the most west. And then you go the next number, it's flipping over 0 hours, 2 hours, 5 hours, and goes on from there. So this is how I would order these. I would look at those stars in that order. That makes sense? Okay. Let's see, exercise. So if you guys want, again, there's no requirement for you to do this, but if you want to go ahead and do the same thing that I just did, look at what stars, constellations are up there. Here's the tables you can use to make a list of double stars that you might want to look at. I'll probably put together a list of double stars. I won't order them or anything. I'll just put a list of double stars out there and email them out before our lab and let you guys play around with them if you want, to do some more research or not. It's up to you. A nice thing about double stars is the little dip, or the Polaris is a double star. It's a pretty nice, actually, little double star. It's got a pretty bright component, and then there's a real dim one next to it. So it's a good one to make sure your objects are working distant or working properly and everything, and you can see it. So that's the one I have in here as a example. Its separation is 18 arc seconds. And there's a difference of 7.9 magnitudes. So that's a huge difference in brightness between those two. So that's like I said, the form that you can fill in if you want to do your own little research. Let's backtrack again and let me write a couple of things. Yeah, we got time. So let's go through this process real briefly for a couple of the constellations. So constellations that we decided were well positioned was Bootes, COO, and CRB. And Draco is going to be up there. And even Virgo might be a good one. Virgo and Liberty and Lupus. Okay, so we'll just start off with that. And we'll come down here, this list here. And this is by no means an extensive list. I mean, generally they think that 85% of stars in the night sky are double star systems. May not be visually double star systems, but double star systems anyway. So here we're going through Andromeda, TRI. Not sure what that one is. Perseus, EU, Orion, Auriga, Orion, Lepus. There's one. So we've got Lepus's constellation that's up. So you might want to look at Gamma. I think that's Gamma. Lepus. So that would be one I would look at possibly. Canis Major, no CN. I think that's Cancer there. Coma was another one. And so 24 Coma might be one that we'd want to look at. There's Eta Bootes. Another one. I don't know why we didn't see Hercules. Where's Hercules at? Because I know it's rising, so Hercules should be on that list somewhere. Let's see where it's at. HDR. There's Hercules. Over in here in June. Yeah, it is rising a little later. So, but still. So there's two in Hercules. If you wanted to do these later in the evening, these would be good ones. Lyra, Cygnus, Capricorn, Cepheus. So that's about it. So we got about 5 prospects. Hercules is a couple more. That's where I'd start at. Does that make sense what I'm doing here so far? Okay. And after you do that, you just write those numbers down in a table like here: constellation, the star, brightest ascent, declination, magnitude. And from that, you can order the bright ascension. That's your viewing order. And just from these numbers, you can pretty much guess what you're going to see. Well, now what this is not telling you is if it's a colored star or something. Actually, this table up here does indicate, maybe that doesn't indicate it. But anyway, this is supposed to be colorful stars. So that's used pretty liberally. Although some of these multiple star systems can be pretty fantastic looking as far as the color contrast, but not many of them are that great. Mostly they look like green colored stars or white stars, you know, nothing that exciting. And that's pretty much our lab. These labs are getting loosey-goosey, and that's because, especially the last 2 labs, it's more of just go for it type of thing. So I'm hoping you guys take some time out to try to figure out what you want to look at, you know, with stuff and go exploring on your own also. But I'll still give a list of stuff that's interesting, but it's pretty much, you know, let you do what you want. And if you have any troubles, contact, you know, ask me questions. Any questions on the lab?
I have a quick question.
Sure.
I'm not sure that I understand about the Greek alphabet. Why is that tied to those objects?
Oh, yeah. No, that's an excellent question. So there's so much information in astronomy, you know, so many different systems. It's really hard to keep track of all this stuff. So to me, it's not so hard because I've been doing it for how many years? 30, 40 years. So that's another thing. So the naming convention, again, it's not fully consistent, but as a general rule, the main conventions for constellations, stars and constellations are they'll start with the brightest star is Alpha. So Alpha Lyra would be the brightest star in that constellation, right? And again, it's not fully consistent, but that's generally the rule. Beta would be the next brightest star, Gamma, Delta, and so forth. So that's why you're getting Eta Bootes. So that was saying that Eta, which one's Eta? Epsilon, is it? Is that Epsilon or Eta? It must, oh, that's Epsilon, I guess.
Yeah.
The way they write these letters are a little different here, but okay. So Epsilon, that means it's 1, 2, 3, 4, the 5th brightest star in the constellation of, of that thing. Now, that's an excellent question. Now, what happens? You know, there's not 24 letters in the Greek alphabet. What happens? There's many constellations with more than 24 letters or stars in it. So what happens when you run out of the Greek alphabet? Then you start numbering them. So then the next star after Omega in a constellation would be 1, whatever the constellation, and 2, 3. So this 24 Coma Berenices here, that's a 24, 24, that's the 48th brightest star in the constellation. Great question there, Jeff.
Thanks. Yeah, thanks for explaining that. I appreciate it.
Yeah. again, just remember, nothing is fully consistent because there are exceptions to where like they named a star Alpha, even though it's not the brightest star, but it's the most prominent for some reason. You know, it was in lore or something like that. So, but in general, that's how it falls. Any other questions anybody has on this stuff? Okay, just a reminder, next week's Zoom meeting, which is the 28th, is not going to be on the 28th. It's going to be on the 30th because I'll be out observing up in the Mogollon Rim. So just to remind you that, also in that email to remind everyone also, but just want to make sure you don't forget about that. Otherwise, we will see, we'll probably, instead of going to the grassy area like we did last week, sorry, confused you guys that we did, we're going to go back over to the dirt area because those lights in the grass area are just a little too distracting. We'll go back to the dirt area over at Gilbert. And then after that, the rest of the labs will be at Picket Post. Adeline, have you decided if and which week you're going to come out, if you're going to join us?
I'm not sure I can make it this time.
Okay.
The weeks seem to be flying by, so.
Yeah, well, it's like that when you're retired, huh? It gets busier.
But at least this week I plan on going camping, so I get to take my telescope away from the city.
Okay, well, that's great. Now, the chair going camping, my recommendation would be, let's see, go into the website. Let's remember on the first lab or first class we had, if we go into the beginner's guide, this astronomy cheat sheet here, clicking on that and scrolling down, there's a potential
Yes.
objects for small telescopes.
Okay.
You might want to look at this because this is going to be stuff that you might be able to see. These bolded themes are really good stuff. So Mizar is a pretty nice little multiple star system. That's one we can look at next week or this week coming in. That's in Ursa Major.
Okay.
So anyway, yeah, this is a good list to use. And again, now you know how to use it more. And here's the, use this meridian transit to figure out what's going to be the ones you want to look at in this list and find out what you want to look at. So,
Yes.
okay, any other general questions before we wrap it up for tonight? Okay, everybody, thanks for attending, and we will see you Saturday at 8 p.m.
All right,
Good
thank you.
night.
See you then.
Thank you.
All right.
Have a good evening.
Bye.